Okay, so this talk was originally given at the Helsinki workshop on quantum gravity in June 2016, and by request of the organizers, it was on a paper written last year, and the topic of the paper was on how to make progress in AdS CFT using loop quantum gravity. And it's mainly kind of a rather heuristic suggestion of how loop quantum gravity can fit into the business of AdS CFT. And what I want to discuss in this talk is the main idea of this and what are the main problems and how they can potentially be solved. So let me give a brief outline of this talk. As usual, I start with some motivation. I will then overview both string theory and loop quantum gravity very briefly on a single slide each, just pointing out the main ingredients of the theory and what they compute. And this will be important just to see that the two theories, there are two theories of quantum gravity, but they're very different in construction and they also compute different things. So it's actually very hard to make a comparison between them. Now, it will then be argued that using AdS CFT, you actually have the potential to make a bridge between the two theories, because AdS CFT gives you kind of a non-perturbative formulation of string theory, where in particular more of the geometry aspects of string theory are pronounced, for example, properties of certain geometric objects like areas in the bulk. Then I want to discuss what are the prospects for using loop quantum gravity in AdS CFT, in particular where it would fit in and what we could in principle compute with that. We will then see that there are several difficulties because loop quantum gravity is in its current formulation rather different than, say, classical gravity or AdS CFT in general. However, I want to then show that there actually exists already a prototype model, which is a duality between a 2D Ising model and 3D quantum gravity with vanishing cosmological constant, where the problems that one encounters, or let's say many of the problems that one encounters in this business are actually solved, and you can show that it really makes sense to try to look for some duality between loop quantum gravity and some field theory on a boundary. Okay, so let us start then with the talk. So first, for motivation, we are interested here in quantum gravity, and by now there are many approaches to quantum gravity on the market. Also, many of those were discussed in this Helsinki workshop on quantum gravity. For example, there's string theory, there's loop quantum gravity, there's asymptotic safety, there's causal dynamic triangulations, and there are many others, like, for example, causal sets and so forth. Actually, if you go to Wikipedia and look at the list that they list for quantum gravity approaches, then it's actually quite an extensive list, and it would be kind of hard to fit them all on this slide. However, in this talk, we'll just focus on two of those approaches, which is string theory and loop quantum gravity. And then the idea will be, well, how could you make some progress in comparing the two approaches? Because if you look at this diagram here, I mean, all of these approaches want to arrive at the same goal. So it would be interesting to check if there's actually some convergence, because if there's not, then we're kind of in a real problem here. Now, another thing that you're, of course, interested in is experimental evidence for your theory of quantum gravity. And this is in general hard. I mean, there's, of course, the field of quantum gravity phenomenology, and people are thinking hard of how you could measure quantum gravity effects. And there are actually many proposals like modified dispersion relations or signatures in the cosmic microwave background and so forth. However, so far there is no direct evidence for quantum gravity, and therefore one might also look for some other applications of your theory of quantum gravity. Now, exactly this has been provided by the AdS CFT correspondence. And the AdS CFT correspondence essentially tells you that if you have some theory of quantum gravity on an AdS space, then this is conjectured to be exactly dual to some conformal field theory on the boundary of that space. And then what you can do is you can just compare what you obtain for this conformal field theory on the boundary to an experiment. And this experiment here, let's just denote it by experiment prime, just because it's not a classical or not a quantum gravity experiment in the usual sense where you measure kind of the quantum properties of space-time. However, it's an experiment which you compute, or the result of which you compute using quantum gravity techniques However, it's then not a quantum gravity experiment, but you map it to some other theory via this correspondence and then check to some more traditional field theory experiment. Okay. Good. So let us start now with string theory in a nutshell. So the main idea of string theory is to replace the point particle concept by the concept of a string. The string can then vibrate, and the different vibration modes of the string give you different particles. And in particular, this ansatz of replacing the point particle by some extended object solves for you some of the UV problems that you encounter in the usual field theories. Now you take your string and you kind of quantize it and you propagate it on some given background and you check the quantum theory. In particular, you check for consistency. And what you find is that the theory, including supersymmetry, is only consistent if you propagate it on a 10-dimensional background. And also this background has to satisfy the Einstein equations of 10-dimensional supergravity theory. So in this sense, you find that this assumption that there should be a string and you should quantize it, it kind of gives you a critical dimension, and it also gives you the Einstein equations in the sense that it tells you that the background on which you propagate should satisfy those Einstein equations. So a typical computation that you do in string theory would be, for example, the scattering of two strings. They are depicted as these circles here. For example, those could be gravitons. And then in order to compute the scattering amplitude, what you compute is a certain sum of diagrams. And the diagrams look like in this picture here. They're called world sheets. So you connect the incoming and outgoing strings by a two-dimensional surface. And then there's an amplitude that you can compute corresponding to that surface. And then what you have to do is you have to sum overall surfaces which connect the string. In particular, you have to sum overall kind of genuses of the surface, for example, with one hole and then many holes. And kind of the coupling constant that controls this expansion is called the string coupling, which tells you how likely it is that a string splits and rejoins. Okay. So then the two relevant parameters in this business are the string length and the string coupling. The string coupling we just discussed. The string length is the parameter which tells you what is the average size of the string. You can also reformulate it as a tension of the string. And basically, if you're well above the string length, then you can regard this string as point particles in a good approximation and have such an approximation for your theory. So an important problem which is kind of open in string theory is a non-perturbative formulation of the theory. So this string scattering that is depicted above, that is only a perturbative formulation, so you need to sum up all these diagrams. However, one is also interested in kind of non-perturbative aspects of the theory, and there's kind of a gap so far. Now, there has been important progress in that with the advent of AdS CFT and also D-branes recently. However, I think it's still fair to say that the kind of non-perturbative sector of string theory is not well understood at the moment. Okay, so now let's proceed to loop quantum gravity. So loop quantum gravity is derived as a quantization of general relativity plus matter fields. Now this is different than previously in string theory, because in string theory we just assumed that there's a string and we checked its quantum properties and showed that in a certain classical limit you find a general relativity. Here you do kind of the inverse. You take a general relativity as your classical theory and you go through some quantization procedure, for example canonical quantization or a path integral quantization, and then you arrive at some quantum theory. Now, in this business, you also assume kind of no background space-time. So in the string, we put it on some background space-time and propagate it. Here, you just quantize the complete space-time, so the complete metric tensor without any splitting in background and perturbation. If you follow through with this, you arrive at a certain notion of quantum geometries, which is depicted on the right here. So on the right, we see a time slice of our space-time, time slice sigma. And the quantum states that we have in loop quantum gravity, we can give a basis for the Hilbert space, and such a basis is labeled by such graphs, which are depicted here. The graph has edges and it has vertices. And what you're then interested in is, for example, what are or how do geometric operators act on such a quantum state. And what you find is, if you compute the area of for example, the gray surface on the right, and this holonomy is labeled by some quantum number lambda, then you find that the area of some area that you compute is only non-vanishing if this area is punctured by one of the edges of your graph, and the eigenvalue is then given by this quantum number. And similarly, if you want to compute the volume of a certain box, for example, say the one also in this picture, then you get a non-vanishing contribution only if a vertex of your graph is inside of this box, and the contribution that you get will then depend on the quantum number which is associated to this vertex. And these quantum numbers, they are just irreducible, they are just invariant tensors in the gauge group that you have. So a typical computation then would be, for example, to compute the properties of these quantum geometries, for example, compute the spectra of volumes or areas, or also to compute certain transition amplitudes between two quantum geometries. And the quantum geometry here I would just refer to a state in the Hilbert space, which is labeled by such a graph with the quantum numbers, which you can roughly interpret as some sort of discrete geometry. And then you can, for example, compute the transition amplitude between one such geometry with another such geometry. So the dimension and matter content here is actually of your choice. So far we have not encountered any obstacles in quantizing in certain dimensions or using certain matter fields, save for some very exotic matter fields that you encounter in some supergravities like non-abelian tensor fields. We have not seen how to quantize those so far, but the rest, the more standard fields in the more standard supergravities and also in the standard model, you can deal with them here. Okay. So if you now want to draw a comparison between the two theories, what you see is that loop quantum gravity and string theory, they compute very different quantities. So in string theory we for example compute a scattering amplitude between two gravitons, which are perturbations of a certain background spacetime. However, in loop quantum gravity, we compute really transition amplitudes of the whole spacetime itself, where there is no split in background or non-background. In particular, quantum states which are under good computational control, so in particular you can handle them on when you do like actual computations. In string theory, they would be the scattering of like a few strings with each other, so a few perturbations on your background. However, in loop quantum gravity, this would really be quantum geometries which are kind of described at a very coarse level. So you have, say, few quanta of space and an area which are glued together to form some big space-time. So these are actually very large quanta, and we have under good control, and we can do some manipulations there. However, if we would now try to approximate something like a perturbation over some background in loop quantum gravity, then we would need really a very, very, very fine state, and that is then, of course, associated with very, very much computational power that we would need to invest. So therefore, the theories compute two different quantities, and for progress, we either need to make some more progress in computing particle scattering in loop quantum gravity, or we need to make progress in kind of computing the properties of quantum geometry in string theory. And now the point A, so far we have not made progress there. However, for point B, we can now use the AdS CFT correspondence, because this correspondence really provides you with computational tools to make some statement about the quantum geometry sector of a string theory, not by a computation within string theory, but by computations in the dual gauge theory. Okay, so let me briefly mention how AdS CFT roughly works. Now, the AdS CFT correspondence was originally conjectured by Maldacena, and then important following works were made by the people cited up in the right. And it's important to say that this is really a conjectured exact equivalence, so there's no proof yet. And it's a conjectured exact equivalence between a string theory on a certain background. It's AdS 5 times S5, and this is conjectured to be exactly dual to a super Young-Mills theory on the boundary of that space, which it turns out to be four-dimensional. It's a conformal boundary of the AdS space, and it's also maximally supersymmetric, so it has this curly n equal to 4, which is the maximal number of supersymmetries that you have in 4 dimensions. Both theories are then determined by two coupling constants, we have the string coupling and the string tension, which is related to the string length on the left, and we have the Young-Mills coupling and the number of colors on the right. And then there are some equations relating them, which are written in the middle here. Now at this level, or at this kind of most general level of the correspondence, it's very hard to test this correspondence just because it's very hard to make general computations in both string theory and also field theory. And therefore, in practice, what people usually do is they take certain limits. For example, on the left-hand side, they take a weak string coupling, which then kind of leaves you only with tree diagrams. And then they also consider strong string tension, which kind of decouples the higher string modes. And then an appropriate description of his string theory is just typed to be supergravity on this spacetime. On the right-hand side, this corresponds to taking weak Young-Mills coupling and also strong Toft coupling. Now, the Toft coupling is this combination G Young-Mills squared and C, which is the kind of relevant coupling for theories which with a very number of colors. And then the appropriate description is, well, this n equals to 4 super Young-Mills theory at strong Toft coupling and vanishing Young-Mills coupling, which is also equivalent to say at a large number of colors, NC. And now at this low energy level, the correspondence is actually very well tested. You can do many computations, for example, in supergravity, or which is just classical gravity in this sense. And therefore, kind of the main use nowadays of this correspondence is to make computations in classical gravity on this lower level, and then map them to some computations in the field theory. So to give a brief example of how this works, now in order to kind of say that you have a duality, you actually need to establish a certain dictionary between things that you compute on both sides. So you have on the one hand your AdS space, the conformal diagram is depicted here, it's a cylinder, and then on the boundary of the cylinder there is your conformal field theory. So then what you want is you want a dictionary which relates observables that you compute in the bulk, so in the AdS spacetime, with some observables that you have on the boundary, so in your conformal field theory. Now it's important to say that this is really a work in progress to establish this dictionary. It is not known completely. In fact, many things are missing there. And if you look on the archive, then continuously you find new papers explaining new entries in this dictionary, so how to compute things in the same way on the boundary and in the bulk. For us here, it's of great importance that this dictionary actually contains certain geometric entries. With geometric entries, I mean they refer to some geometric structures in the bulk. And one of them, which I just want to mention here, is the Ryo-Takayanagi prescription. Originally, it was proposed by those people. Then there are several generalizations of this, which are also important. But here, let me just mention for the sake of simplicity, this original prescription. So what you do is you consider some time slice in your AdS space, this gray area here. And then let's just look at this time slice. On such a time slice, well, you have your boundary, and on the boundary you can select a certain region depicted here in red. And if you select a region of your boundary, one thing that you compute is, for example, the entanglement entropy associated to that region. And then the Ryo-Takayanagi prescription tells you that you can also compute this entanglement entropy by computing a minimal area in the bulk of your spacetime whose boundary coincides with the boundary of this red region. And then it turns out, of course, that this minimal area is actually codimension 2 area in spacetime. And well, the correspondence then says you can compute this area, and if you have this area, you can also infer from this the entanglement entropy. Now this is of course very interesting because in loop quantum gravity something that we can compute is, for example, the spectra of certain areas, for example also such an area that we would just draw in here. So now the question is, where could loop quantum gravity fit into this business? I just mentioned we see here that there's a good possibility to compute something similar from both approaches now. So roughly, well, loop quantum gravity, it's a theory of quantum gravity and some prescribed theory of well, gravity that you quantize. So for example, you could take just a supergravity in 10 dimensions and quantize that. So how would that fit into string theory, or how could that fit into string theory? So string theory roughly is a theory of quantum gravity. However, it's not just this theory of quantum gravity, but it's more, it has an infinite tower of particles that come on top of that, which are given by these higher string states. So therefore, naively, if you would now like to connect this to a quantum supergravity that you have, what you would need to do is you would want to kind of neglect the stringiness of your theory, so neglect all these higher string modes, however retain the quantumness of the theory, because, well, you want to describe this quantum theory. Now, the free parameter that you would like to keep would be kind of the number of colors, because this is associated with the quantumness here. And this number of colors squared by the AdS CFT dictionary, this is just the kind of scale or the length scale of the AdS divided by the 10-dimensional Newton constant. And if you want to express that in the parameters of string theory, this G10 is just the string coupling squared times the string length to the power 8. So therefore, roughly what you would like to do is you would neglect stringiness, which would correspond to taking this LS to 0, so that the higher string modes decouple, the string tension becomes infinite. However, you would like to keep this NC fixed, so you would actually need to take a strong coupling limit GS to infinity and see how this works. Now there's a problem with this in string theory, as was pointed out to me by experts, which is that this limit is kind of funny in string theory, because if you would naively do that, then you would get some light kind of brain states, which would, or some heavy brain states would become light in this limit and kind of replace the fundamental strength. So it's kind of not really clear how exactly this works in string theory, and in which areas this limit provides a good approximation. However, what is very noteworthy here is that this kind of, if you would have an expansion in NC squared or in NC, this really corresponds to what you find in loop quantum gravity, which is the large spin expansion. So this the ratio L to the 8 divided by G10, this is what you would call a spin in a 10-dimensional loop quantum gravity. It's not really a spin, because spin is just something that you find in 3+1 dimensions. However, it would be the quantum number of your kind of the fundamental quantum number of your gauge group. This would be exactly computing codimension 2 in space-time area, and this is what you find by this L8 over G10. So therefore, if you take some fixed graph state in loop quantum gravity and you perform an expansion in a large spin, this would actually correspond to this expansion in NC squared. So therefore, the naive or kind of heuristic statement here is that if you kind of do the expansion that people do in loop quantum gravity, which they do to arrive at a classical limit, this would kind of correspond to this 1 over NC expansion in the dual gauge theory. Now, as said, this argument was actually very heuristic. It has many potential pitfalls which are not explored yet. However, I think it's worth really looking in more detail into this, in particular also because people are already using quantum supergravity to make some predictions for or some predictions in AdS CFT. However, they don't use some non-perturbative quantum supergravity as it is suggested here, but some just a perturbative quantum supergravity in the more traditional sense. So let me mention some general problems of using loop quantum gravity for AdS CFT, which we have so far. And the picture that you should think about when you think about this is kind of the picture on the right here. So we have this AdS space, again, given by this cylinder, and you put a time slice there. And on this time slice, you put a quantum state, which is well, given by this graph there, or some spin network defined on that graph. And well, the main point is, well, this quantum state is discrete, so it gives you some discretization of the bulk, and it also induces some discretization on the boundary. So therefore, if you use states that we have under, say, good control in loop quantum gravity, or appropriate control, which are states defined on a single graph, then what you would actually need is some discrete version of the AdS CFT dictionary, just because by such a state, actually your boundary is discrete and also your bulk is discrete. So this then raises the question, of course, of how to bridge to the usual formulation of AdS-CFT, this would require to take some continuum limit in loop quantum gravity. This is kind of the main construction side of the theory, and this is what is not known. And therefore, we have to kind of leave this question open so far, and we should first focus on this discrete version of AdS-CFT that we may construct. Another problem to mention is that, loop quantum gravity is mainly used in 3+1 dimensions. It's only a rather recent development that you can go to higher dimensions. This was mainly in the canonical formalism. So in order to apply this to more kind of entries that you find in the AdS-CFT dictionaries, we would also need to generalize spin forms to higher dimensions. Spin forms are just a kind of path integral formulation of loop quantum gravity, and they're mainly done only in 3+1 dimensions. There's a work on higher dimensions, but it's kind of using some older techniques which are or have been surpassed by some more appropriate definitions in 3+1 dimensions, so one would also need to generalize that to higher dimensions. Also, we would need to treat properly AdS spaces in loop quantum gravity. There is some work of that, essentially by performing some conformal rescaling so that you can really use some finite state as depicted on the right here to kind of define an AdS space. However, there's still more work needed to understand the details there. Also, some general problem, which is not really restricted to loop quantum gravity here, is to have proper quantum gravity generalizations of this AdS-CFT dictionary. The point is there that many of the entries that you find are actually formulated at the level of classical gravity. For example, if they tell you to compute the area of some minimal surface, for example, this is something that you really compute in classical gravity. And it's not at all clear in many cases how to generalize that properly to the quantum level, just because, I mean, the question is, what is the proper analog of a minimal surface area in the quantum theory? And just to say some more details on this, the question, for example, arises in this Ryu-Takayanagi business. And there you could naively say, well, maybe it's just the, if I have an area operator, it's just the area that minimizes this area operator. And people have thought about such questions in the AdS-CFT literature, and it turns out, interestingly, that what seems to be the good way to do it would be to minimize not something corresponding to the area, but minimize the entanglement entropy in the bulk, so not on the boundary, but on the bulk, and that would be the proper quantum generalization of this state. So this is arrived at by looking at certain inequalities which entanglement entropy has to satisfy, and then prove that this is kind of the good way to do it. So this is just to show that there's actually a big uncertainty here, also already from the AdS side, which is to think about how quantum gravity really fits in exactly in AdS-CFT. So let me now, as kind of the last thing, discuss some prototype duality between what you could call 3D loop quantum gravity, which is the Ponzano-Regge model, and the 2D Ising model. And this is kind of a prototype duality which shows you that you can actually formulate AdS-CFT at such a discrete level that makes sense in this context, and you can give certain dualities. So this is essentially something that follows from work of Dietrich and Nuvida, and also Bonsomme, Constantino, and Levin. So the statement there is that if you have a certain boundary state in your quantum gravity model, this maps you, or the kind of the on-shell amplitude of that, it maps you, or it is given by certain parameters, and these parameters map to the couplings and the lattice that you have in an Ising model. So the quantum gravity state on the boundary, it defines uniquely an Ising model on the boundary. It gives you kind of a lattice on which the Ising model is defined, and gives you the couplings which are on this lattice. Now you can compute the partition functions in both cases, and you find that they match in the following sense, that they satisfy this equation below. So if you take the Ising partition function squared and then the spin partition function and multiply them, then you get some very simple function of the involved couplings. So these are just the couplings which determine the boundary state and the Ising model couplings. And now if you have such a relation here, it's of course immediate to derive some dualities, so you can just take certain derivatives of this relation, and then you find that you can compute the Ising correlators in terms of the expectation values of the spins on the boundary in your quantum gravity model. So this is really a correspondence at the discrete level here, and there is no continuum limit taken so far. Something that is not clear so far at this point is whether you can also extend this dictionary to some bulk observables. So if you define some bulk observables in the quantum gravity model, which has been done, then there's no entry in this dictionary so far on how to compute them using some computation with the Ising model. So this duality then, as said, it kind of shows that you can in principle do something like a duality between a theory of quantum gravity formulated a la low quantum gravity to some field theory. It turns out then that since there's a certain discreteness in the quantum gravity theory, there's also discreteness in the boundary theory. And in principle, this might even help you to now look at the continuum limit in the bulk theory, just because you know how to take continuum limits in bulk theory, in the boundary theory, because I mean a lot is known on the 2D Ising model. In particular, there's also some work on dualities of the Ising model with the other theories of quantum gravity. There's an interesting work on showing a duality of the Ising model described by a conformal field theory, so only at the critical point, to a quantum gravity with a negative cosmological constant in 3 dimensions. And it would be very interesting, of course, to compare the results here to the results there. Okay, so let me, to finish, briefly mention some problems that can be worked on, or problems that need to be worked on. As said before, one needs to generalize this AdS CFT dictionary to quantum gravity settings. You also want to establish some discrete dictionary, if in case your quantum gravity theory is discrete, as in the or has some discrete structures in the Hilbert space. We should be more precise. I mean, the statement is not that LQG is kind of discrete; it's that there is a certain basis in the Hilbert space that we control well, which has an interpretation of discrete geometries. We have this kind of prototype example of 2D, 3D correspondence. It would be very important to generalize this to higher dimensions. In particular, one has to check like how this generalization works. For example, we need a conjecture. What is a good dual to a 3D Ising model? Would it be, again, a topological theory like 3D quantum gravity, or would it already be some kind of gravity theory, so a theory with bulk degrees of freedom? One needs to investigate the continuum limit. It might be very useful to do this by using a boundary dual, just because a lot more is known on taking continuum limits in, for example, statistical physics or condensed matter. Of course, we need to find computations that can actually be done, so this is always a problem. So you need to find computations that can really be done in LQG with some kind of feasible amount of computing power. And this Ryo Takayanagi was just mentioned here just because it kind of computes what is kind of the most fundamental observable in loop quantum gravity, which is codimension 2 area in spacetime. Also, it would be interesting to compare this then to the results that people found using perturbative quantum supergravity in AdS CFT and see if there's a convergence or not. But yeah, of course, the hope in this using loop quantum gravity in this business is that you can actually compute things that you cannot compute in perturbative quantum supergravity, so that you can really go beyond what people did so far. Okay, just to mention previous interesting work, work of Laurent Fredel, work of Bonsom and Dietrich, and also ongoing work by Jeff Nubida. Okay, so let me briefly conclude the talk now. We've outlined that there's actually a need to go beyond classical gravity in using AdS CFT, just because you're interested in theories with a finite number of colors, and for this you exactly need this quantumness of gravity, and classical gravity is not enough. We've shown that loop quantum gravity has the necessary structure to be a candidate theory to compute those corrections. However, it was also mentioned that the argument made there is somewhat heuristic and may need to be refined. However, it gives you some starting point in giving you a non-perturbative formulation of quantum supergravity where you can start looking at those things. The whole thing is largely uncharted territory. It's not clear how to proceed or which directions are most fruitful. However, in this business, there are many chances to learn about quantum gravity, also about loop quantum gravity, because many of the problems that you need to look at here are kind of also core open problems in loop quantum gravity, and therefore you would kind of not waste your time if the connection to AdS CFT would fail to exist. In general, everything here is high risk, high reward. So high risk because, well, as said, it might not work to use LQG for AdS CFT, or it might turn out to be more complicated. However, of course, we would still learn about AQG. But if you can get it to work, then it would be very high reward, because then you have a kind of more useful tool to compute these 1/n corrections for AdS CFT. So let me therefore thank you very much for your attention. And of course, I'm always very interested in comments on this topic, especially by people who are experts in string theory. Well, I would be very happy to receive those comments. So thank you very much.